Welcome back. We are in lecture 3 of Fundamental of Electronics. The topic that we are going to discuss is on diode circuits. Previous few lecture we discussed on the introduction of electronics with the diode theory. In this lecture we will focus on diode circuits. The lecture is divided into few subparts which will cover the entire aspects of diode circuits. Let us see the introduction first. Generally, the electronic system, such as if you talk about the high definition TVs, audio amplifiers, the computers, which required a DC voltage to operate efficiently. Since the requirement is the DC voltage, but the power line voltage is basically alternating. So we have a single phase AC supply that we get at our household. So the DC voltage requirement may not be met because the AC voltage are typically too high, so it must be converted. So we need to convert the AC voltage into DC voltage, which is the prime requirement, and these requirement will be filled up with the use of the rectifiers, and the rectifier will be needed the diode. So the key components of a power supply is the voltage reduction. Voltage reduction generally mean that we need to have a less voltage because the supply voltage is high, and we need a suitable level of the voltage which is in the form of DC. So we need to bring the voltage down with the help of certain device which is known as voltage reduction. Then the second step would be to convert the DC conversion. Since the supply is AC, which we have brought out into laser voltage, we need a constant DC output. So a device is required to convert the AC to DC. Third, we have requirement of power supply unit. The section of these electronic system is responsible for generating the DC voltage. The DC voltage requirement that we have may not be in the form of pure DC, it may be fluctuating DC, but with the help of the pure DC output we need, and we get it with the help of certain devices which are known as filters and the regulators. So power supply unit includes various internal circuits that will function in different ways to get the desired constant DC output. When we talk about the internal circuits of a power supply, we first require the rectifier. The rectifier function is to allow the current to flow in one direction. So it is basically converting the AC voltage to the DC voltage. The DC voltage that we get at the output of the rectifier is not the pure DC. So we may be requiring the filters which will smooth out the fluctuations which are there in the DC output. It ensures a steady and consistent DC voltage. The filters also need one more device, that is the regulators, which are the voltage regulators. It will maintain a constant DC voltage because the output of the filter may not be giving you a constant DC. It may be smooth, but it may not be constant, whereas voltage regulator give a constant DC voltage despite the variations in the input or the load conditions. So whatever the load variations may come or the input supply voltage variation may come, but the output of the regulator will give you the constant DC voltage. Other circuits that also required, and we will discuss, those are basically the clipper circuit, the clamper circuit, and the voltage multipliers. Clippers are basically used to modify the shape of the voltage waveform. Clampers shift the voltage level of the waveform from one level to another, and the voltage multiplier increases the voltage to a much higher level. So these are other type of circuits that we discuss under the category of rectifier diode circuits. So the chapter will essentially discuss the power supply that will include the rectifier, filter, voltage regulators, clipper, clampers, and the voltage multipliers. So here we can see through the diagram that if you have the AC input, which is basically the single phase AC input with high voltage, generally in the volt of 220 to 230 volt. So here you have the voltage which is AC higher voltage 220 to 230 volt. We bring this voltage to a laser level with the help of the step down transformer. So we will discuss the transformer in very brief here. like how the transformer can bring the voltage from 230 volt to a working voltage like 5 to 10 volt here and the output of the transformer. So these input will be given to the rectifier. So rectifier here the input will be AC, which will give you the DC output and the output of the rectifier. But this DC, if you can see that it is fluctuating, it is not smooth. For smoothing we require the filter. So the output that we get it is much smoother from using the filter, but it may not give you a constant DC voltage. So at the output of the regulator, we will be getting the constant DC voltage, which will be given to the load in the electronics. If this load is fluctuating, then also the voltage will be constant using the regulator. So this chapter, if we discuss the outline of the diode rectifier circuits, we will discuss the half-wave rectifier and the full-wave rectifier. Again, the full-wave rectifier may be center-tapped or bridge rectifier. We will discuss the filter in the form of the choke input filter or the capacitor input filter. What is peak inverse voltage in the diode and the surge current? Other type of power supply topics we have. Clipper circuit, which are again the limiters, clampers and the voltage multipliers. So these are the different parts of the lecture 3. So we are in lecture 3 and we will discuss these subtopics into different parts. In this part, we will focus on half-wave rectifier in detail. So let's start with half-wave rectifier circuit. So here the given figure we have, which is half-wave rectifier circuit with an AC source. So if you see the input which is given is basically the AC source, and there is a diode which is connected, and you will be getting the output across the load register. So the AC source produces a sinusoidal voltage. We know that you will be having a single phase AC source which is in the form of sinusoidal voltage. The positive half cycle in the AC wave, if you see, it will forward bias the diode. So this diode will be forward biased. So we have discussed in detail what is the meaning of forward biased and reverse biased in the previous lectures. So the diode will be forward biased in the positive half cycle, and as the switch is closed, so this will behave as the diode is on or the switch is closed. Positive half cycle appear across the load register, and you will be getting the unidirectional load current. So current will be flowing from the source to the load as if the switch is closed or the diode is on. But when we talk about the negative half cycle in AC wave, it will reverse bias the diode. So this diode will be in the off state. The idle diode act as open switch. So you will be having the configuration as open switch, which represent the reverse biasing of the diode, and there will be no voltage which appear across the load register. So since the diode is open, so no current will be flowing here. No current is flowing, I equal to 0, because it is open circuit. So the voltage is also 0 in the load register. When we talk about the waveform of the half-wave rectifier, so the input voltage waveform is basically a sine wave. So that is AC with an instantaneous value given as V input with a peak value Vp. So we can see that it is a sine wave with multiple cycle with positive and negative, with the maximum value we can take as Vp with the input voltage given as the single phase AC supply. A pure sinusoid has an average value of 0 over 1 cycle. So if we talk about the 1 cycle on the wave, its average value will be 0 because the positive and negative will cancel each other. Each instantaneous voltage has an equal and opposite voltage half the cycle later, and hence the DC voltmeter reading will show you the 0, which indicate the average value. So if we are using a DC voltmeter and the reading is showing 0, it means we are talking about the average value. So here we have the diode, which is in the form of ideal diode. In the forward bias condition, this diode will be on and you will be getting the output voltage. So here we can see the positive will give you the voltage when the positive you have on the AC input. On the negative input which you have on the AC cycle, there is no waveform here and you do not get any waveform. And during the negative half, another positive half cycle of the next half cycle, you will get again the output and then 0, then positive and again 0. If we observe that this is unidirectional, but it is not smooth or neither the constant. The maximum reverse voltage that the diode will withstand is again the negative of V maximum, that is Vp. So this is the maximum reverse voltage that the diode will have to withstand when the diode is reverse biased. So in this case, the figure V, which is the indicator of diode conducting during the positive half cycle and does not conduct during the negative half cycle. So the diode will conduct only in the positive half cycle. And the figure C, this figure will indicate that the circuit clips off the negative half cycle. You are not getting any negative half cycle portion in the output voltage, producing a half wave signal. The half wave voltage produce unidirectional load current. So whatever the current is flowing, this is unidirectional. The current cannot flow in the reverse path because the diode only conduct in one direction. If the diode were reverse bias, it would become forward bias during the negative half cycle and output pulse would be negative. So if we take the reverse biasing of the diode, then in that case, you will have the negative half cycle and negative half cycle will appear across the diode, and the diode has to withstand the maximum negative half cycle voltage. The characteristic of half wave signal is basically the pulsating DC voltage, which we have seen the output of the rectifier, and this characteristic is to increase to a maximum value, decrease to 0 and remains at 0 during the negative half cycle. So we can see that you will be having only one half cycle which is positive, it will increase to maximum, and then you will be having 0. Then it will be 0 and then it remains at 0 during the negative half cycle, and then you will be having another half cycle. So this is the characteristic of half-wave rectifier. This is not the constant DC voltage which is needed for the electronic equipment. So you are not basically getting the constant DC voltage. To get the constant DC voltage, you again require the filters and the regulators. So to obtain the constant voltage like a battery, filtering of the half-wave signal is required, which we will discuss in detail later in the topic. If we talk about the troubleshooting, we require the ideal diode, which analyze the half-wave rectifier. So whenever you have a practical diode circuit, you basically connect it with ideal diode to analyze if certain fault is there in the circuit. And the peak output voltage is equal to peak input voltage. So whatever the output voltage you will get it in the ideal half wave, it is equal to the input. There is no power loss in the diode. The DC value of the half wave signal, if we talk about it, is equal to the average value of the signal. So average value of the AC wave is 0, but the DC wave we will get certain average value. This formula which we can calculate the DC value for the half wave is given by Vp by pi. So Vp is the maximum value and pi is a constant. So 1 by pi we know 0.318 we will get approximation. So we can say that the average formula of DC is equal to 0.318 into the maximum AC input voltage. So if you have the AC input voltage whose maximum value is given as Vp, the average output DC voltage is 0.318 Vp. So if the input voltage maximum is 100 volt, then the output you will get as 31.8 volt as the average value. In some case, we need to find the RMS, that is a root mean square. So root mean square voltage is 1.57 times the average value. So the average value is equal to the DC value, which is equal to 0.318 times Vp. And the alternate formula of RMS we can calculate from sine wave concept, that the maximum value by root 2 times, which is 0.707 times the maximum voltage. So this formula also we can use it to find the RMS voltage. RMS value represent the DC value that produce the same heating effect as the AC waveform. So this concept we have discussed very detailed in the topic of the basic electrical engineering and the electrical circuits, where we have compared what is the meaning of a root mean square RMS value and what is the meaning of DC value. So it produces the same heating effect, and we in AC we talk mostly on RMS, and DC we talk only on the average side. If we talk about the frequency, so it will have the same frequency because whatever the output frequency we have, it is equal to the input frequency. In the input of the rectifier, if the input we are having at 60 Hz, then the output of the transformer will be 60 Hz only with lesser magnitude. So each input cycle produces one output cycle. So this gives the frequency output of the rectifier circuits. When we talk about the second approximation method, which is basically there will be certain cutoff voltage of the diode. So you have the forward voltage of the diode which conduct only when the input voltage is greater than 0.7 volt. We have discussed this in very detail, like for a silicon diode or a germanium diode, what is the minimum threshold level of the voltage after which the diode will conduct. So if, and in the ideal state this will be 0 volt, but in the practical state we will take 0.7 volt. So the adjusted voltage by second approximation method, we are getting the equation which is the output voltage maximum is equal to input voltage maximum, and we are subtracting this 0.7, which is not required in case of the ideal diode. So if the input voltage is 5 volt, then the output voltage you will not get 5 volt but 0.7 volt less, which is equal to 4.3 volt. If we take one example from the lab of a half-wave rectifier, let us see how to do that. You have a source which is AC 10 volt, and this is the RMS. The frequency, if it is 60 Hz, then using one diode, you can get the output as DC. So what is this value of the DC that we will get it? If we want to validate, let us connect the output with oscilloscope, which is a digital storage oscilloscope, and one multimeter. So multimeter also give you the current value. So we can have the output to find like what is the value of the voltage and the current at the output. So if the source voltage is 10 volt, which is RMS, we have to first calculate the peak voltage, because it is the peak voltage which will be used for the calculation purpose. So we know the relationship that RMS voltage is 0.707 times the peak voltage. So peak voltage we can obtain from this equation as the RMS by 0.707, which gives us 14.1 volt. So this is the maximum peak source input voltage. Now, if the diode is idle, then the peak load voltage, whatever you have at the output, so you at the output you will be having a load resistor. So here the output voltage is nothing but whatever the input voltage you have obtained, the maximum value, that is 14.1 volt. The DC load voltage, we have seen the formula is Vp by pi, which gives us 4.49 volt. So it means that if the AC input maximum is 14.1 and the output we are getting 4.49 volt. But this is for the ideal diode. For a practical diode, we have to add the second approximation method, by which we have to subtract 0.7 volt from the output. So 4.49 we will not get because we get a little bit less of this 0.7. So the maximum voltage is 14.1. We have to subtract the 0.7 volt. We have 13.4 volt now. Now these 13.4 volt we have to divide with pi. So it is 4.27 volt. So with ideal diode output is 4.49. But with practical diode we are getting 4.27, which is including the losses of 0.7 volt which we required for the diode to conduct. Now, what is the use of transformers in the electronics? Let us see. If we talk about the United States, nominal line voltage, we have 120 volt RMS at 60 Hz. This voltage is basically in another country like India, we have 230 volt RMS at 50 Hz frequency. So different countries will have different RMS voltage and different frequency. Usually 60 Hz and 50 Hz are the one which is being used by most of the countries. So actual voltage may vary from 105 to 125. So when we talk 120, we do not say it is exactly 120, but it is a variation from 105 to 125. We require a transformer generally to step down the line voltage to a safer level for electronics. Electronics generally require very less voltage, but the supply voltage is quite high, which can damage the circuit when we talk about the diodes or the transistors in the electronics. Hence, we require the transformers. So we know the transformers will have the primary winding, which will be connected with the supply. So this is the primary winding, and the secondary winding will be connected to the load, and you have a supply which is basically the AC. So this voltage, if we talk about 120 volt, 60 Hz, then using a step down transformer, and here the output of the secondary, we will be getting a voltage V2 is equal to N2 by N1 into V1, where V1 is basically the supply voltage and number of turns on the secondary side is N2 and number of turns on the primary side is N1. So we have V2 equal to N2 by N1 into V1. So this is the voltage V2 which we are getting at the secondary of the transformer, and this diode, when it will conduct, if it is a practical diode, again we have some threshold value, and then this voltage will be little bit less from the secondary output. The dots plays a very important role because unless until we know the actual direction of the current. So when you have a transformer, there will be dots given which represent the mutual induction, whether the current is entering or current is leaving. This dot can be positioned in different places in the primary winding and secondary winding. It can have the position like this. So dot ends have the same phase. Positive half cycle on the primary will give you the positive half cycle on the secondary. If the dots were on the opposite end, secondary voltage would be 180 degree out of phase. So generally we require the dot like this, which is on the same phase. If the dots are opposite, then you will be having 180 degree out of phase. Half-wave rectification, positive half cycle diode will be forward biased, and the negative half cycle the diode will be reverse biased, and the result you will get the half-wave load voltage. What you required is basically a transformer, and transformer can be step up or step down, but it is the step down transformer which generally used in electronics. We don't need a step up transformer because the voltage is quite high. But from the concept side, we say that step up transformer is the one where the secondary voltage is greater than the primary voltage, and step down transformer is the one where the secondary voltage is less than the primary voltage. So electronics, we will be using the step down transformer to bring the AC voltage to a safer level. Let us take one example with the help of a transformer to understand this half-wave rectification principle. So here you have the AC input, which is 120 volt 60 Hz, and you have a transformer which is 5:1. It means that number of turns, if we take 5 on the primary side, the secondary will be having 1 turn. So we can easily see that there is a step down of the voltage. And there is a load resistor which is connected, and the output of the diode load resistor value is 1 kilo ohm. So what is the voltage that you get at the secondary V2? So V2 is equal to, you have the step down transformation ratio of 5. So we have 5:1. So here the input is 120 volt. So 120 volt divided by 5, we get 24 volt as the output of the transformer on the secondary side. So but this is what we have the RMS. So we need the maximum value, which is we divide with 0.707, which gives us 34 volt. So the maximum voltage of V2 is 34 volt, and with the diode we convert it into DC, and the average value we get Vp by pi, so we get 10.8 volt. Remember, this is again the ideal diode for this calculation purpose. But if you want the practical diode, the output voltage which we get is 34 volt, which is here the V2 maximum, minus some threshold level on the diode, which is 0.7 volt. So we have 33.3 volt, and these 33.3 volt we divide with pi to get the actual DC voltage waveform voltage. So here we have 10.6 volt. So there is little difference between the ideal diode and the practical diode. So in the ideal diode we have 10.8, but in the practical diode condition we have 10.6 volt. So this complete the first part of the diode circuits. We discussed the half-wave rectifier here. In the next lecture, we will focus on full-wave rectifier having the center tap transformer and the bridge rectifier. Thank you for now. See you in the next lecture.